So today lecture objectives are to calculate the energy difference and probability of finding the electron. And in one of the two previous lectures about the solution of the Schrodinger wave equation with the particle in one-dimensional box, we have already calculated the and derived the energy, the quantization of the energy, and an equation for the probability of finding the electron. So today we will use some sort of the data to calculate all these two objectives, and one of them is the energy difference and the other one is the probability of finding the electron. So the data is given over here. So first understand what is written over here. This is an data for an electron and for the nitrogen molecule. And an electron is placed in one-dimensional box that has a length of zero point 0.1 nanometer. And this 0.1 nanometer, it is the size of an atom. So the first question is calculate the energy difference between N2 and N1, and these are the energy levels. The energy difference between energy level 1 and energy level 2, and in a similar way you can do the calculation for any of the energy levels, particularly for the transitions between energy level 1 and 2 to 3 or 1 to 3 and so on. Any of the energy level you can calculate the energy difference, and that is the quantization of the energy. And this is very important because in one of the next lecture we will be calculating the wavelength as well by using this quantization of energy, and this is very helpful to understand the electronic transitions in UV visible spectrophotometer. So particularly this would be the application of the solution of the Schrodinger wave equation with the direction in one-dimensional box. And the second part of this question is we are going to repeat the same calculation for the nitrogen molecule in a container whose length is 10 centimeter. So look at, this is the length of 0.1 nanometer and this is the 10 centimeter, and this is the length in which electron is placed, and with this length the nitrogen molecules are placed. So later on we will compare actually what we are going to do here with the quantum mechanics or the classical mechanics. So this would be our final conclusion after calculation of uh, the uh, uh, the energy difference for an electron in zero point 0.1 nanometer length, and for the nitrogen molecule having which is contained in the 10 centimeter length. So third part of this question is important. We will calculate the probability of finding electron, and these are the limits of the box, and it would be between x0 and x L by 2. That means half of the total length. So for the energy level 1, and similarly you can do the calculation for the energy level 2 and so on. Sorry. So let's start with the first part, very simple to calculate. And this is the equation we have already derived, and this was the quantization of the energy in any of the level. N is the energy level, H is the Planck's constant, 8m is the mass, and here in this case mass of the electron or the mass of the nitrogen molecule, and L is the length of the box in which the electron or the nitrogen molecule is placed. So by using this, we will calculate the energy difference, and this is the simple equation to calculate the difference in energy. That would be E2 minus E1. E2 is the energy level 2 and E1 is the energy level 1. And similarly, you can there are two way, maybe you can calculate separately, and at the end you can just subtract the energy level 2 minus energy level 1, or you can do at the same time. And here I am just putting the E2 over here, and E2 in this case is the energy level 2, so N is the value 2 and this is the N value 1, and the rest of the parameters are the constant. And if you take a common over here, this is the 2 square equal to 4 minus 1, and this all will remain the constant. So this is the easiest way. There is no need to multiply this constant factor with the both time. So you can calculate by using this one, and the answer of this one is the 1.8 x minus 17 joule. So it is always most important to keep in mind the unit conversions over here, because if you are not placing the right unit, you would not be able to get the accurate or the correct answer. So all here the units are in the SI system. Here the unit of let's the Planck constant is joule second, and the square is would be the joule square second square, and here kilogram. And again this is the zero point 0.1 nanometer, the length of the box, and you have to convert into the meter, and 1 nanometer will be equal to exponent 9 minus 9 meter. And this is the just a very simple way to use this the units cancellation method to because this is the numerator denominator, it would be cancelled out, and 1 x1 minus 9 meters left. So this is the just to convert the nanometer into meter, and then look what would be the rest of the unit. This is the energy, and energy must having the unit of the energy, and this is in joule, because here the Planck's constant, the joule is written over here. So when this in the denominator, kilogram meter square per second square will be equal to joule. So here this is a kilogram, this would be the meter square, and this would be the, it is in reverse, per second square. So this all unit will be equal to joule, and this is already joule square. So 1 joule square divided by joule is cancelled out, and 1 is left, and that would be the final unit of the energy. So in this way, again, I am going to more focus on the units, and you must use the appropriate unit to get the correct answer. Second part of this question is we are going to calculate the same energy, the difference in energy, by using the mass of the nitrogen molecule. And here there is no need to actually to give the data of all these, the mass of the electron or the mass of the nitrogen, because these are the standard values, you must know these values. And again, for your simplicity, I am just putting here again a very basic conversion, because again at this level there is no need, but to just keep in mind how we are going to get this 4.65 exponent minus 26 unit. So this is the nitrogen one. Nitrogen is having the 14 molecular mass, and for the N2 there is should be a 28 gram per mole, and you must have to convert the gram into the kilogram, because we are using the SI system over 1 kilogram will be equal to 1000 gram. So gram is cancelled out. This is the unit conversion method. Again, you have to get the mass of one molecule, so you must use the Avogadro number. So these 6.02 exponent 23 molecule will be equal to 1 mole, and again this mole is cancelled out, one is left one. This is the, if you will calculate, that value will be equal to 4.65 exponent minus 26 kilogram per mole. So this is the mass of the one molecule of the nitrogen gas. And again, rest all these are the same. You would be using the same energy levels, Planck's constant, the mass of the this one, the mass of the nitrogen molecule. And again, remember, the data was given about the length of the box or the container was the 10 centimeter. So you have to again convert the centimeter into meter, and 1 centimeter will be equal to x minus 2 meter, or 1 meter will be equal to 100 centimeter. You can put any of the conversion factor over here because it will give you the same answer. So again, 1 centimeter, 1 centimeter is cancelled out, meter is left, and then there is the same unit conversion over here. You will get the value of 3.5 x minus 40 joule. So let's see actually what this value is giving you, the significance of this value, the energy difference in case of the nitrogen molecule, which is placed in the 10 centimeter container, and this was the energy difference when the electron was placed in zero point 0.1 nanometer. That means one is the micro state and the other one is the macro state, or you can say the quantum mechanics or the classical mechanics. So this is the outcome, or you can say this is the comparison between these two, uh, the energy difference between the uh, electron and the nitrogen molecule. So this energy difference is around 23 orders of the magnitude less than as we have calculated in part A. And remember, this is the translational energy because we are considering the particle in one-dimensional box, or we are using the energy. That energy is particularly with the translational energy, as we have already derived by using these assumptions to calculate the quantization of energy in case of the translational movement of the molecules or the electron. So this energy for the nitrogen molecule is somehow 23 order less in magnitude the energy of the electron. So that means this is insignificant difference between the energy level. You may say 3.5x minus 40. This is much less difference as compared to the electron which was placed in the zero point 0.1 nanometer a box, or that was the size of the atom. So what does it mean? That means the energy of the nitrogen molecule varies essentially constant. That means it is not quantized. So that is the basically difference between the quantum mechanics and the classical mechanics, as we have discussed in first one of the starting lecture of this course. So this result confirms that our earlier statement that when molecules are confined to a macroscopic system, their translation motions are governed by the classical mechanics, so not by the quantum mechanics. In a similar way, we have already done with the de Broglie equation, the wave-like properties of the particle, and there we calculated the both of the wave-like properties of the electron and the for the tennis ball or the football, that and there we also concluded that particularly this equation is for the microscopic system or the quantum mechanics, not for the classical mechanics. So this is again the assumption, or we are again forcing our knowledge over here. That means the this energy difference is confirmed that this is the macroscopic system, not the quantum system. And when it is the macroscopic system, so translation energy should be governed by the classical mechanics, not by the quantum mechanics. Third part of this one is the to find the probability that the electron will be found between these limit x0 and xl by 2, and Just to remind, I have again put the picture over here. So this is the length of the box starting from the 0, ending with the L, and maybe the any of the value over here. So this is the in between. There may be a probability of the finding electron that the maximum probability would be equal to 1. So this was the formula we already discussed in the second part or the third part of the translation motion with the particle in one dimensional box, and we have already derived the wave function. uh, by using this equation you can calculate the wave function, and when you take the square of this one, that would be equal to the probability. So in one of the previous lecture, actually we have already derived and discussed all these two equation. This is the probability of the wave function, and or you may say probability amplitude of the wave function, and this is the probability density of the electron, or you may say probability of finding the electron in anywhere within the box. You can use this formula, and here actually we are using this formula to understand and to calculate where would be the probability density of the electron, where actually is the position of the electron within the box if we apply these limitations. And here we are again restricting our calculation to energy level 1, and in a similar way you can do the calculation for the energy level 2, 3, and so on, but remember we are starting with the energy level 1. And this is the when you have this type of the equation, as we use the mathematic formula again. Actually we have simplified this one with the integration. You are going to integrate by using the formula. This is the sine square pi over L x and dx, and we are actually integrating the x is the any of the distance between this box, and this is the x direction, and any of the x would be the any value between this box, and and this is the same as written over here, and n is not over here because we are calculating the probability with the energy level 1. So if you put the value 1, this will be pi over L. So this is there is no difference over here, just the replacement of this equation by using the integration sign with the limit starting from 0 to L by 2. And actually this is the formula we used earlier to derive this equation, and we are going to use this formula to calculate the probability density. And why we are going to use, because in a direct way this is not giving you the solution, and we are using a mathematical expression, and this was about the normalization of the wave function. So this is the formula we are going to use, and because whenever there is the sine square, this constant x, and this is the, let's suppose this n pi over L is the a, x is there, and dx representing, that means you are going to integrate the x, which is the variable over here, a is the constant, and this is the same formula over here. When you having this type of the expression, and this is the solution of this integration, that would be equal to x by 2 minus sine 2ax and 4a. And here the x is the any of the distance between the box, and here we are going to use x is equal to 0 and x equal to L by 2. So where would be the maximum probability of the electron? And if you put the value of our all limitation over here, so again a over a is the constant and pi over L, and when you put the value of n, so L will a would be pi over L, and the limits are x0 and xl by 2. So you must have to put all these your values over here. So this is the x by 2, same is written over here. So let's see, later on I will put the value of x over here. Actually x is the there are two limitation. X is l by 2 and x is 0. So here you have to put x l by 2 minus sine 2. Again a is the this constant, and here it is the pi over L, and then x is the same over here, and in the denominator this is 4a, and again a is the pi over L. And now you put the value of the limitation of this integration, which is starting from the 0 ending with the L by 2. So this is the maximum, this is the minimum, that is the integration sign over here. So now I'm going to put the value of x. When you put the value of x over 0 over here, and this is x L by 2. So this is the solution of this one. 2 over L is coming from the equation. X is L by 2 sine n by this whole, when you multiply with the 0, this whole factor will become 0, and sine 0 will be equal to 0 again. So that's why this whole factor will become 0, and what is left? 2 over L. X is L by 2 divided by 2. 2 is cancelled out. Again L is cancelled out, and 1 over 2 is left. That is the solution of this part, and that mean this is the probability of finding the electron between x and xl by 2 when you have the energy level 1, and it would be 1 by 2. And this is explained over here. We also used this diagram before. So this is the energy level 1. When you have the energy level 1, and this is the also energy level 1, this is the wave function, and these are the probability of the finding the electron. So the total distance from here to here is the L. That means starting from 0 ending with the L, and half of this one would be the L by 2. And if you have a look over this is the half, and maximum probability of finding the electron is over here. That means the when energy level is 1, then the maximum probability would be at half of the distance of the box, and that is the L by 2. And this is the 0.5, as we have already said before. Maximum probability would be the 1, and it would be the half of the box, and the maximum probability by using this limitation over here, and that is the expected value in the classical as well as the quantum mechanics, because there is no such other factor regarding like mass of the particle is given over here. So you can apply this equation for both of the quantum and the classical mechanics to find out the probability of the finding electron. So this is all about our today lecture.